Hello everyone, today I'm going to give a talk on our STOC 22 paper, Optimal of Vertex Connectivity Oracles. First, the introduction. In our work, we assume the graphs are undirected and unweighted. And for the K-vertex connectivity oracle, it's an oracle that answers pairwise vertex connectivity if it's below K. Namely, it's answering the minimum of K and the minimum vertex cup between U and V for two vertices. And we studied this oracle in three aspects: the space, the query time, and the pre-processing time. We will prove a space lower bound, and we'll design an oracle that matches the space lower bound and also have good query and pre-processing time. About the space lower bound, we showed a lower bound of omega kn bits. And the basic idea is, first, we focus on the case of k equals to n. And for the general case, you can make n over k copies of n so that you obtain an omega kn lower bound. And for this special case, we construct 2 to the omega n squared graphs such that the value for our target are distinct among all these graphs. And how to construct these graphs? We first construct 2 to the n squared over 3 matrices. All these matrices have row weight n over 2, and their pairwise Hamilton are all at least n squared over 3. And how to do this? We just generate random matrices. For 2 matrices, if their Hamilton is too close, then they will match in at least many terms, much more than their expectation n squared over 2. So by Chernoff bound, there are only negligible fraction of them. So if you just generate random matrices, you can throw away only negligible fractions, and then you would have that their pairwise Hamilton is at least 2n squared over 5. And how about the row weights? By the in expectation, each row would have weight n over 2, and if it's deviating of about n squared, then by Chernoff bound, the probability is negligible. So we only need, for most of the matrices, we need to modify n to the 3 over 2 terms, and the others are only negligible fractions of them. So because 2 over 5 minus small n is still larger than 1/3, so we have this matrices. And the second step is, for each matrix, we find 2 matrices A and B. A is of size n times Cn, B is of size Cn times n. And in the product of AB, if it's larger than 2n, we mark the term of t hat as 1 and otherwise 0. And we want that t and t hat has time distance at most n squared over 6. Here, C is a constant that we would specify in the proof. And the way to do this is we just first randomly generate B. So think of a row of T. Then with constant probability, although very, very small, but constant probability that a row of B will agree with a row of T on at least n over 2 plus square root of n terms. And in such rows, we place 1 at the corresponding position of A. Then if you think of the product of A times B, if you set C sufficiently large, then by the Chernoff bound, the t hat would be sufficiently close to T. And you can set the constant so that it's at most n squared over 6. And the third step is, for each A and B, you construct a tripartite graph of size C plus 2 times n. It has 3 partites, x, y, and z. X and z are of size n, and y is of size cn. And you connect the vertices between x and y with respect to the matrix A. and you connect the vertices between Y and Z with respect to the matrix B. And for the vertices in X and Z, the vertex connectivity between them, whether their vertex connectivity is larger than 4n minus 2 is equal to the matrix T hat. And we will prove this by, you can think of in this graph, the contribution of the vertex connectivity between U and V. It's by Munger's theorem, the number of paths, vertex disjoint paths between U and V. The length 2 paths are from X to Y and to Z. And this is exactly the term of UV in the product of matrix A times B. And because this is an undirected graph, there are some paths of length at least 4, such as from X to Y to X, and then to Y and then to Z, or from X to Y to Z, and to Y and then to Z. But they must cross the other vertices in X and our other vertices in Z. And we show that if you switch random OC log n edges in X times Y, then all these paths are always full. So first, because of the limits in X and Z, there are at most 2n minus 2 of them. And we show that if you switch such edges, there are always 2n minus 2 paths there. So now we constructed 2 to the n squared out of 3 graphs. And if you think of this indicator of these graphs, they form matrices. And these matrices are distinct because they are close to each t, and those t's, their pairwise time distance is large. And in this way, we prove a lower bound of omega n squared. So about oracle design, how do we design an oracle that matches the space lower bound and give a good query time and construction time? We can first think of a very similar problem, the Gomeroi-Hu tree, which is a very old and famous result. It answers the edge connectivity between arbitrary 2 vertices. And there were a long line of work in the history talking about this. And it turned out that the Gomeroi-Hu tree does not directly applies to the vertex connectivity. However, there is another intermediate, that is the element connectivity. You first find a set, fix a set that is called the terminals. We call them the terminal sets. Then the element connectivity for 2 terminal vertices is the minimum cut, which consists of edges and non-terminal vertices. And the properties of the element connectivity is that it has Gomeroi-Hu trees, and it's a generalization of vertex connectivity. And we noticed that in some literatures, it's also called the S connectivity. So now we can use the element connectivity to exploit the power of Gomeroi-Hu tree, and also generalize the vertex connectivity so it can support the queries to the vertex connectivity. And this is by the building block lemma. It says for 2 terminals, the element connectivity is always at least as the vertex connectivity. And if there is a vertex minimum cut that does not contain any terminal vertices, then this inequality takes equality. Because if the intersection is empty, then CUV is itself an element cut. So suppose you form the terminal set by sampling each vertex with probability 1/k. Then by simple calculations, you will find that with constant probability, the element connectivity equals to the vertex connectivity. So if you repeat for log n times, then with high probability, the minimum element connectivity equals to the vertex connectivity. The minimum here, by the minimum, I mean the minimum over the O log n copies. So suppose you randomly sample OK² log n Gomeroi-Hu trees. Then for 2 vertices, there is with constant probability that some terminal set contains both of them. And their minimum vertex cut is disjoint from the terminal set, then that terminal set, if you build a Gomerhole tree for it, it can answer the vertex connectivity between U and V. And that is our oracle design. And we can see that it takes nk log n space, so it matches the lower bound. And it's important to note that it is equivalent to the labeling scheme in the work that is 10 years ago. But our improvement is about the query time and the construction time. Let's first talk about the query time. We improved the query time from k log n to log n. And why is that? Because among the k square log n terminal sets, you need to find which contains both U and V. You can store which vertices contains which terminal sets contains U, and that can be potentially k log n of them. And there is no way to make it better, so you must search among at least k log n terminal sets. The essence for this is that you're actually brute forcefully searching which terminal sets contains both U and V. So a way to improve the query time is, suppose we can compute exactly which terminal set contains them. And this is our design. That is, we used hash functions and the find plane. So that's for each two vertices, whether they are, which terminal set contains them, we can find them and then we can index it in O1 time. The design is, first you find two large primes and you hash the vertices into the x coordinate of size n over k, and the y coordinate is of size k. And then you enumerate the lines of all the slopes, all possible slopes, and all possible intercepts. The slopes can take values from 1 through k, so it's k of them, and the intercepts can value from 1 through k. So there are k-square lines, and each line would contain n over k vertices. For each line, you build, for the vertices it crosses, you build a element connectivity Gomerhole tree with the terminal sets as the vertices that the line crosses. So for any two vertices, you can use O1 time to compute which line crosses them. And then you can find a terminal set that contains both of them. And with constant probability, it would equal to the vertex connectivity. So if you make log n copies of them, and for each copy, you take O1 time to find which terminal set contains both of them. So it only takes O log n time, so that the probability is high. Then we improve the query time into O log n. So how about the construction time? The construction time equals to the constructing the Gomerhole trees for all these k-square log n copies, and each of them is of size n over k. So the problem is how to efficiently construct a Gomerhole tree for the element connectivity. And actually, last year in STOC 21, there is an algorithm that computes approximate 1 plus epsilon edge Gomerhole tree in maximum flow time. And if we pick epsilon into 1 over k, then it can also answer exact below k queries for edge connectivities. And we only need to think of how their algorithm can adapt to the case of element connectivity. But this is not trivial. There are some obstacles. The obstacles in adapting them is, although I'm not going deep into their actual algorithms, but we can go into their basic frameworks. In their algorithm, there is a recursion that, suppose you find a global minimum cut S that splits the graph into L and R. Then it does a recursion that split into the subcases of L and R. Actually, in the subcase of L, they shrink R into a single vertex. And for the case of R, they shrink L into a single vertex. And then it recurses down so that the running time is as expected. But for the element connectivity case, if you have a global minimum element cut S that splits the graph into L and R, then if you think of the subcase of L, the two vertices X, Y in L, then the minimum cut between them may contain some edges or vertices in R. And the most important problem is that the minimum element connectivity for XY in L is not equal to their element connectivity in G, the larger graph. And how we bypass this is in the subcase of L, we don't shrink R, and we mark terminals in R as forbidden. And then by some sophisticated lemmas, we prove that in this case, in the subcase, the element connectivity equals to the original case. And how do we use these forbidden vertices? In the algorithm, actually, there is a step that invokes the maximum flow algorithm. And in that step, we make the forbidden vertices with a vertex that has capacity at least k, that is placing k parallel edges to replace that vertex. This would result in this would make that the forbidden vertices would never appear in the cuts that output by the maximum flow algorithm. So that's in the subcase of L, the minimum element connect cuts are actually the minimum cuts in the original graph. So R does not affect the results in L. So the recursion is valid, and we can still get the similar time bound. And this is about the construction time. So in conclusion, in the problem, in our problem of K vertex connectivity oracle, we proved an space lower bound of omega km, and we constructed an oracle whose size is O kn log n, which matches this space lower bound, and its query time is O log n, which is currently best, and the preprocessing time is k times the maximum flow of size nk. And if you use the currently best maximum flow algorithm, it's n to the 4/3 times k to the 7/3. And we can discuss about some future directions. First is, suppose you augment cut to connectivity queries. That is, you not only want the value of the minimum vertex cut between two vertices, you also want Oracle to output a cut. And in our case, we can augment the cuts to the Gomrihu trees. In each Gomrihu tree, it has actually n over k cuts. So, and there are k squared log n of them. So there are nk log n cuts, and each cut takes OK space. So taking the product, this will result in OK squared n log n space. But actually, information theoretically, the lower bound is just omega nk. So there can be some improvements. And the second future direction can be the special case when kappa g equals k minus 1. That is, suppose the graph is actually k minus 1 connected, and you want to locate all the k cuts. This is a work that we had before, and actually you can restate it as how to answer whether two vertices are disconnected by a global min cut. And the third future direction can be we are not limiting the size, but we can think of the approximate vertex cuts. That is, we do not think of the limiting it as the cut size is below k, but we answer whether we can have an 1 plus epsilon approximate for vertex connectivity. For example, whether you can answer 1000 approximate vertex connectivity. Actually, we already have this for element connectivity because we have 1 plus epsilon approximate element connectivity common tree. So they can support approximate element connectivity queries. But there is a gap between the element connectivity and the vertex connectivity, because in the 1 plus epsilon approximate case, the cuts can potentially be of size ON, so that some of the methods becomes invalid. And these are the 3 future directions. Thank you for listening.